So what's precision? Precision is how accurately you can measure something. Some scale might measure to only 1/10 of a gram, and some scale, if you buy a really expensive one, might measure to 1/1000th of a gram. So it's how closely you can measure things. The ruler that you got in first grade probably didn't go that far down into inches, but you could get something. You could get a laser rangefinder that might go down to the thousandths of an inch, and that would be more precise. Accuracy is how well it measures how close to the correct answer it is, how close to the correct answer, because you could have something that says it's measuring very well, but is actually giving the wrong answer, and that would be not accurate to give the wrong answer. On number three, my classic example that you are free to feed back to me is a scale that reads out to 1/1000th of a gram, but it was dropped and now it gives the wrong answer. So it looks like it's precise and it's built to be precise, but it's giving the wrong answer now because it's reading things wrong. Number four, percent error. What we're going to do is actually, I'm going to go over to my other example that I made over here, because here's one that involves percent error. So percent error is needed because just because you missed something doesn't mean you did a terrible job. So if you were supposed to get an answer when you measured something of 1,000 and you got 1,005, that's actually a pretty good job. If you were supposed to get 10 and you got 5, then missing it by 5 is a pretty bad job. So we don't just say we missed it by 5 or missed it by 2, we define it based on what you should have gotten. How much did you miss it by? What percent did you miss it by? So here's an example. If you were supposed to get 10 and you got 12, then you missed it by 2. And if you're supposed to get 10 and you got 8, you missed it by 2. And I want to make a further point here. In both cases, that's 20% error, because what we're going to do is take what you, I'll do the 12 one here, what you got minus what you should have gotten. And actually there's absolute value bars here for all you math people, remembering that? So I just take big minus small. You could also do, if you got 8, you could do 10 minus 8 on the top there. You can do big minus small, because if you get a negative number, we're just going to call it positive, because that's what absolute value does. We just want to know how much you missed it by, not if you missed it high or low. So if you're supposed to get 10 and you got 8, we're just going to call that missed it by 2 and not too negative, not too negative. We're just going to call it positive 2 either way. And then what you do is you divide it by what you should have gotten. That's what I meant by if you were supposed to get 1,000, then when you go and divide by 1,000, it makes your error look really small. And since we know that we missed it by 2, 2 over 10, and then times 100 makes a percentage, gives us a 20% error. So both of these would be 20% error because they both missed it by 2, and then we would divide by what we should have gotten, and then times 100 makes it a percent. So hit pause and give that a think and a rewind, and give me an email if you still don't get it. Also, percent error is all over YouTube. So if the accepted density is this and you got this, what's your percent error? Now, you'll find it written out on the internet in different ways, but again, it's absolute value bars. So just take big minus small over what it should have been. Now that's where I usually get an error, is I get kids dividing by what they got, but it's by what the accepted answer is. And in this case, the units would cancel out. So I just start to not put them in. Usually I'm really, really picky about the units, but we would get grams per milliliter over grams per milliliter, and they would cancel out. So there's kind of no point. So 22.7 minus 22.1, and now I'm going to make an important point here. I have made this mistake myself. You have to hit equals next. You can't just continue dividing. The calculator will do things out of order. You have to hit equals and get the subtraction answer right now, and then you can divide by what you were supposed to get, divided by 22.7. And then times 100 makes it a percentage, and that puts the decimal over here, or you can just punch it in yourself. So 2.6% error. And we are going to use units, and I sent out an email about this, or excuse me, I made a post on Classroom about this. We're going to use units, so don't just put 2.6. It's percent error. That's what we're finding. How many significant figures are in your percent error and why? Well, I am going to assume that you had like a chem class that went over this, and in fact, most of you were in my chem class. So what we got up here, if you remember, in our calculator is 0.6. So you know what? I'm going to have to amend this, and I'm going to have to say 0.6 is my, was up here, this is 0.6. So I get 0.6 over that. So I'm going to have to round this off to 3 because I have a 1 significant figure number over a 4. So 1 sig fig. Why? Because the subtraction answer gives 1 significant figure number. So what are the fundamental international system or SI units for measuring the universe? And by the way, back when they started this thing, all the sophisticated, educated people also took French. So it was named in French. So that's why it's SI, because if you're speaking French, it would be SI, not IS. So we talk about the SI units. Now, these are the fundamental units that don't depend on anything else, and we just basically made them up. Now, when I say quantity, I mean what's the idea, the concept that's being measured? And then what's the unit and what's the symbol that we write? And so you can hit pause. So I'm going to just read through these in case you can't read my writing, but there's nothing else really to discuss. I admit this is a memorization question, but sometimes we just have to memorize things. So we measure length with meters, which is small m, mass with kilogram, which is kg, volume with liters, which is usually capital L, which is a little weird because it's not a person's name, temperature with Kelvin, and that's a capital K because there was a Lord Kelvin, current with ampere, which is a capital A because there was a Mr. Ampere, time with seconds, which is just small s, that's not a capital, and luminous intensity, in other words, the strength of a light, the intensity of light with candela, which is CD, small c, small d. So these are common prefixes. Again, kind of a memorization question. Remember that this is my notation for 1 times 10 to the minus 9. That's the same thing, but it's much easier to write this, and I write this way a lot, but they all translate out like this in case your teacher wrote them like this. So nano multiplies 1 by 1 billionth, or you can write 1 over a billion, write out the numbers, but I'll also take the word in English, billionth, multiplies by 1 billionth. Micro multiplies by 1 millionth with an M. Milli multiplies by 1,000th. Now we go up instead of down. We're going to get bigger than 1. Kilo multiplies by 1,000. Mega multiplies by 1 million, giga multiplies by 1 billion, and tera multiplies by 1 trillion. So what does a liter measure? This is actually a lot of repeat here. It measures volume, and is it based on anything? No, it's not. It's there because we said it is. A milliliter measures volume, and it's 1/1000th of a liter, isn't it? A meter measures length, and that's all there is to it. A kilometer measures length, and it's 1,000 meters. A centimeter measures length, and it's 1/100th of a meter. A millimeter measures length, and it's 1/1000th of a meter. A kilogram measures mass, and now this is a little weird because I did say that the fundamental unit is a kilogram, and this is weird because kilo means 1,000, and the simple fact is, in reality, a gram of something is so small that it's even kind of hard to notice a lot of times. It's like the mass of a paper clip. So what they did was they made it so it sounds like the fundamental unit is gram, but really the fundamental unit, back from the other paper, is kilogram. But what I'm trying to point out is, what does that word mean? So it measures mass, and it's 1,000 grams. That's why they called it kilogram. And a gram also measures mass. A mole measures just things, items, could measure anything, although to be realistic, the only thing you could measure in a mole is molecules and atoms, because we don't have enough of anything else. And it is 6.022 times 10 to the 23rd of something. In the same way that a dozen is 12 somethings, a mole is this many somethings. It's an enormous number. And at least when I was a kid, the estimate of the universe was that there weren't even that many stars. And I looked it up, and there is not even a mole of grains of sand on Earth. That's how big that dumb number is. Celsius measures temperature, and since that's the one that we're used to seeing, I just left it as no definition, although technically Kelvin is the fundamental unit. So Kelvin also measures temperature, and it's Celsius, and when I put capital C here, I mean this, plus 273. So I mean, if you had 100 Celsius, you would have 373 Kelvin. A second measures time, and there's nothing else to say about it. A minute measures time, and it's, of course, 60 seconds. A joule measures energy, and that's about all I'm going to say about that, because otherwise we get really complicated. Torr is another measurement for pressure. And atmosphere also measures pressure. And you know what? I am going to do this and just do that. Number 10, give the formula for density and explain the letters in the formula. So I kind of did it backwards here. Here's the formula, and then I explained it, but whatever. Density is mass over volume. So say a feather has a big volume, or this sheet of paper, right? Its mass is spread out. So the volume it takes up in the universe is big compared to its mass. But a rock has much more mass for volume, so its density is much higher. Or a pool floaty blown up has a high volume and a low mass, so it has low density. So its density equals mass over volume. Now on 11, hit pause and read through it, because I know you can read, and then I'll explain it. Now, we put the rock in the aquarium, and the water went up from, say, here to here. So the volume of the rock is not the volume of the water from the bottom. It's the volume that changed. So the water went up from here to here. So we would multiply. This would be the height, not the whole thing. Just this part would be the height, times the length, times the width into the paper. And that would give us our three-dimensional volume. Now, it doesn't matter which one you label width, height, and length, of course, but I want to point out that I cannot measure from the bottom. I know it went up from here to here. So what I'm going to do is subtract, and that's how I'm going to find this distance is that distance right there, the amount that it rose. And then I can borrow the other two dimensions for my width and length, and there's my height, and I can multiply, and I get the volume of the rock. And this is probably something you did in 6th or 7th grade, to find the volume of an irregular object to do water displacement. Because how are you going to measure a rock? I mean, it's basically impossible, right? But you can make the water do it for you, and it does a very good job. Now, what's the density of the rock? But back here, we said the density is mass per volume. They gave me the mass over here, didn't they? And I just found the volume. By the way, centimeters times centimeters times centimeters is centimeters cubed, which is also exactly the same thing as a milliliter. So I don't care which way you put it. I tend to write milliliters because the chem people usually like milliliters, because then it relates to liters just in the words and stuff. But it's perfectly legitimate either way. Now, also, we would tend to rate this in grams per milliliter, and I already have milliliters. So what I did is I took my kilograms and I turned them to grams, because remember we said up here that there's 1,000 grams per kilogram. So the grams number is always 1,000 times bigger than the kilogram number. It's 3 decimal points bigger than the kilogram number. So take a moment and maybe hit pause, but this number is 3 decimals bigger than that one. So this is grams. And now I just get out my calculator and divide, and I can get 3 significant figures. So there's my 3 significant figures. And don't forget the unit. Nothing cancels out. The unit is grams per milliliter. So then we don't have to just find the density. We can use the density formula to find other things. So I know this is the density formula. Instead, this time on number 12, give it a read. We know the density and we know the grams. What I don't know is the volume. So some people like to solve for the V beforehand, and that's not the way I do it, but you could. So, but I just did it sort of my way, but both are legitimate. So I put the numbers in, and then the V multiplies across and up, and this comes down on the bottom, and this is what I get. Now give that a good think. Or I could do this. If I knew 5 equals 20 over x, doesn't that become x equals 20 over 5? That's what I did. With these, and then get your calculator and you can divide. And this time the grams is going to cancel out and give us milliliters. You might want to hit pause and give 13 a read through a couple times. So she puts the chain in the graduated cylinder, and we know how much it goes up. So we don't have to subtract back like on this one. We know the difference of the height. So they just gave us that. So what's the density of the chain? Well, the density, remember, would be, density is grams per milliliter. So we'll take the grams that they gave us and the milliliters that they gave us, and we divide, and here's the density that she's getting. So what we're going to do is combine that with percent error, and the accepted value is here. So how much did she miss it by? Well, subtraction will tell us how much she missed it by. And then we divide by the number that she should have gotten supposedly. Times 100 makes it a percentage. And there's her percent error. Now, what could have happened to make this error? Well, she missed high, right? Her density is higher than what she should have gotten. And so one of the classic errors, and I would put this down, this would be your classic error, is to do it kind of backward and to put the chain in the water and then take the weight. But if you weigh it wet, then your mass is too high. And that could give her a percent error like this. So what could have happened? She could have weighed it wet, and then her mass would be too high. If you give this a read, now we know that gravity is accepted to be 9.81 meters per second squared anywhere basically on Earth that you're ever going to be, okay? You'll notice that mountain climbers do not report that gravity felt weird. And if you've ever been up to top of Big Bear or Mammoth Mountain or a Pikes Peak or something on a travel, you didn't feel gravity being any different because those mountains are not big enough compared to the whole of Earth that you can notice anything. So if you did some experiment, somebody did, and you get 9.7 meters per second squared instead of 9.81, that is really weirdly low. So should the currently accepted value be called into question? Why or why not? And the answer would be no, because we have thousands of experiments that verify this number. And because just somebody, some local kind of doofus like me got this number doesn't mean that everybody else is wrong. So why not? Because our experiments are extremely verified over many, many, many experiments. What could have happened to give you that value? You probably did the timing of the drop of the object wrong, which is the tough part to do. It's real hard. If you're just using a hand stopwatch or something, it's very, very hard to do. So if you want an example of what could have happened, you could have gotten the timing wrong when you dropped your object to time how long it takes to drop 10 meters or whatever. How many digits are you allowed to use when measuring? And the answer is one more than is visible. And here's my example. Here's my ruler, and it gives me like 1 centimeter, 2, 3, 4, 5. And so I measure my little block or something, and it comes to this point. Now, is it reasonable for me to guess that this is 3.5? And the answer is yes, because it sure isn't 3.1. And it probably isn't 3.2, and I think most people would say it sure isn't 3.3. You might get somebody who says it's 3.4 or something, but 3.5 is a lot better answer than just putting 3. So you are allowed to take one estimate between the marks of the item that you're measuring with. So how many digits are you allowed? One more estimated digit than what is displayed or shown on the measuring device. when measuring your car's miles per gallon, it's more accurate to measure it over 2 miles or 100 miles. Now, you never know what could go wrong. And maybe your gas gauge, your speedometer isn't that accurate, and so forth, or whatever it is, or your odometer that's figuring your miles, I mean. So here's my point. A fundamental principle is it's more accurate to measure more of something than less of something. Because imagine, just for to be dumb, right? You're trying to figure your car's miles per gallon, right? And you just go to the end of the driveway. Well, your numbers are that you're going to measure are so small that you can't even do it, right? Those numbers are just so small they're useless. So what you want is more. I think everybody would agree that the driveway is too small. Well, 2 miles might make it sort of usable, but 100 miles would be even more usable. And any error that crept in just because of something weird going on would get smaller and smaller and smaller in your percent error. So which is it? Over 100 miles. Why? Because measuring more, farther distance or more of something reduces the percent error, tends to reduce the percent error. What's a scientific law? It's something that's been extremely verified and everybody accepts as true. And my classic example is gravity pulls downward, not upward. And if you have a planet this size, at this density, and so forth that you live on, then the strength of gravity, the acceleration of gravity will be 9.81 meters per second squared. And there's some other stuff we could go into, and there's a much bigger equation that accounts for gravity anywhere in the universe. But no one's interested in discussing with you, or arguing, I should say, whether gravity is like true, right? Or how gravity works. It's been verified. Or, what's an electron? We're not really interested in arguing that exactly anymore. It's been verified so many times that if you want to argue about it, you're just kind of, making trouble at this point because it's been verified too much. But a scientific theory is not a law. It's an explanation for the evidence we have at hand. And I would put that down. That's our best explanation for the evidence at hand. And I can differentiate between these two by saying, the scientific law is that gravity pulls down at this acceleration, but the theory is but why. Why does it do that? And those are not the same thing. And our scientific theory has changed over time. And we have what seems to be a pretty good explanation now, because when we make guesses with our theory now, we get right answers from our experiments. So we're pretty confident of that. But there are some other things that we don't have good theories about, and we know. If you've heard of dark energy or dark matter, we don't have good theories. Somebody someday is probably going to win a Nobel Prize and become seriously about as famous as Einstein for explaining these things. We have experiments that show us stuff that no one has a good explanation. We don't have a good scientific theory. And just to go one more step with this, I know that the cop shows on TV talk about theories, and I have a theory and so forth. We're working on the theory that, but basically in those cases, they are kind of abusing the word. They have an explanation, but it's not, based on evidence a lot of times. And basically what they mean is a hunch, just sort of a wild guess. So we do not mean a wild guess. And so when people say, oh, that's just a theory in science, that's not fair, because we have explanations based on evidence. We don't have just wild guesses. Our guesses are called hypotheses, not theories. What's the evidence that our atomic theory is correct? Well, so we have a lot of explanations for a lot of things about atoms and electrons and so forth. And if our explanations were wrong, we couldn't make stuff like cell phones, huh? So we must have a pretty good idea, because somebody went to a lot of trouble to make something like this, and it actually works, and it works really well. And when we use our theories, we keep getting answers and that nature agrees with. And of course, we can't argue with nature. Nature is just nature. So when our theories agree with nature, we count that as correct. And when our atomic theory is used, we get answers that let us build very complicated things, like our electronics. Why would ancient people think that heavy things accelerate faster with gravity than light things? Well, because of course, you would see leaves fall off a tree, and then you could throw a rock, drop a rock, and so forth. because they weren't accounting for wind resistance. And that's the error that little kids make all the time. So because you don't account for the wind resistance, and light things catch a lot of air. Like a parachute is designed to catch a lot of air, so you can just jump a whole person out of a plane, right, and catch so much air that it falls so slowly that it's actually safe. Why is it true that everything tries to accelerate the same with gravity? And this one I didn't understand until even a few years ago. That's why I like this one, because it's a kind of a deep insight that no one bothered to tell me for a while. Now, if you have a rock, I'm going to make a square, and a rock that's twice the mass, okay, twice the size, anyway, we'll pretend anyway, right? Then when gravity tries to pull this, the force, you could say the force is so much, and then this would be double the force because it's double the mass, and that's true. However, this has double the inertia. So I'm going to spell that because I've gotten some weird spellings. Inertia. Now, inertia means how hard something is to push around or pull around. So things that are heavier have more force than gravity, yes, but they also have the same amount of an increase in inertia. So something that's twice as heavy, twice as massive, has twice the force from gravity, but it also has twice the inertia, and it's twice as hard to get going and twice as hard to speed up. So that all cancels out, and everything falls at the same rate. So why is it true that everything tries to accelerate the same with gravity? I mean, except for wind, right? Except for wind resistance, is because more massive things do have more force from gravity, but they also have the same increase in inertia. Or, for example, something twice as massive, you could put, for example, just to make sure that you put something that counts in case your explanation gets a little mangled, something that's twice the mass, has twice the force from gravity, but it also has twice the inertia, which means it's twice as hard to get going and to move. Now, I don't think I knew this one in high school, but how does the effect of gravity change? Read the question. So here's the center of Earth. We're going to stand way, way back and look at Earth as a little dot here. As the circle, and here's the center of Earth, and you're standing on the surface of Earth. So you experience gravity at 1 Earth radius, because halfway across Earth is 1 Earth radius, right? So that's your normal living conditions right here. Now, if you could get off Earth to go 1 more radius away, well, this much again, and we'll pretend that that's a radius. I probably drew it too far, but we'll pretend that this is 2 radii away. What would happen to the effect of gravity is it would be the square of the inverse of the increase. So we increased by double, right? 1 to 2 is double. Well, we take the increase, inverse it, so it's a half, and then square it. So the effect of gravity, the gravity effect, would be 1/4 at 2 Earth radii away. If you went 3 radii away, the increase would be from 1 to 3. That would be triple, or 3 times increase, and the gravity would be the square of 1/3. So it would be 1/9. And then an increase from 1 to 4 would be a multiple of 4. So we invert it, put it 1 over it, and square it, and you would get 1/16 as much gravity. So the phrase that I like to use is, how does gravity change? What's the effect of gravity? It's the square of the inverse of the increase of the distance. It's the square of the inverse. Remember, this is the inverse of that. It's the square of the inverse of the increase, because the increase was a factor of 4, multiple of 4, and we squared the inverse of the multiple of the distance, the increase of the distance.